Hello everyone, welcome back to class. Today we are going to be looking at a very sweet topic in physics, which is the capacitance of a capacitor. Which is the capacitance of a what? A capacitor. Please, I'm taking you guys through what you need to know about capacitors and how to calculate their capacitance. How to define the capacitance of a capacitor and how to know the various types of capacitors we have and how to combine capacitors in reduced cycles. Now, before we go into this topic properly, first thing you do for me now, you must ensure you don't distract yourself by any means, and please subscribe to this channel if you have not done so, and don't skip any part of this video. Don't skip any part of this video, because every second of this video is going to be very effective. So if you want this video to not like affect you in a very good way, don't skip any part of the video. Watch the video from the beginning to the end, and you will be blessed at the end. So let's go to this topic we have here: capacitance of a capacitor. Now, what is a capacitor? What do we mean by a capacitor? A capacitor is a device. A capacitor is a device that stores electric energy or electric charge. That stores electric energy or electric charge. A capacitor can also be called a condenser, which can store electric energy. It can also store, electric energy in the form of electric charges. And to calculate the capacitance of a capacitor, we use the relation C is equals to Q over V. What does that entail? That is telling us that the capacitance of a capacitor is the ratio of charge to potential difference. Is the ratio of what? Charge to what? To potential difference. Or we can also say that the capacitance of a capacitor is the ratio of charge to voltage. The ratio of what? Charge to voltage. So from this mathematical definition now, you see you have here is called the capacitance of a capacitor. The Q you have here is the charge, and the V you have here is either potential difference or voltage. Taking note of that is very, very important. It's very, very important. Now, the plates of the capacitors are always separated by a material called dielectric material. Take note of that. Called what? A dielectric material. A dielectric material. And the dielectric constant of a medium, which is air, is approximately equal to 1. Also take note of that. The dielectric constant of a medium, which is air, is approximately equal to 1. Now, if you have what we call epsilon naught. I don't know if you have seen this before. Epsilon naught. What we call epsilon naught. Now, anytime you see epsilon naught, we already use dielectric constant to multiply epsilon naught in an equation, especially in electricity physics. So, if you have a dielectric constant for a particular capacitor and is greater than 1, you just use dielectric constant to multiply the epsilon naught in the equation of that capacitor. You might say, okay, where is epsilon naught here now? It's not appearing here yet. We are still coming up, and we'll get there, you see it. Almost all the equations we related today, almost everything we have in this epsilon naught, which is called the permittivity of free space. That's what we call it. The permittivity of free space. And this one is a relative permittivity, which is the dielectric constant of the medium in which you are. So if that dielectric constant is greater than 1, it's going to increase the value that you are going to have here, the overall value. And by that, we also increase the capacitance of that capacitor. So think about that. It's very, very important. Now, we have different types of capacitor. We have different types of capacitors, which are number one. Okay, fine. Go there. Let us solve a very simple question. Okay, let us do a little analysis. So take note of this. The SI unit of capacitance, the unit of capacitance is either I say coulomb per volt, or farad, I just use that abbreviation of F to present that, farad. Then, should I use farad or use coulomb per volt for unit of what? Capacitance. And remember, the unit of charge is what? What unit of charge? Coulomb. What unit of potential difference or voltage? Volt. That's the unit. Take note of that. It's very, very important. Very important. Now, let's say we have a question. Calculate the capacitance of a capacitor that holds a total charge. Calculate the capacitance of a capacitor that holds what? That holds a total charge of 20 microcoulomb. That holds a total charge of 20 microcoulomb and a voltage of what? Of 100 volts. A voltage of 100 volts. You can also say, and the potential difference across this capacitor is 100 volts. Let's have it that way. So what would be the capacitance of that capacitor? We said the capacitance of the capacitor is generally defined as what? Charge over what? Voltage or potential difference. So that will be equal to, charge is what? Remember this one is 20, this one is the charge, using coulomb. This one is the voltage or potential difference. This one will be 20 times 10 raised to the power minus 6 coulomb. Why? Because this value here is 10 raised to the power what? Minus 6. That is the meaning of that symbol. This micro, we call it micro in this electric physics. So this micro means 10 raised to the power minus 6. That is the value for that micro. So if you want to substitute this value here now, we're going to have 20 times 10 raised to the power what? Minus 6 over what? 100 divided by 100. Divided by 100. So we can also say, I can say this is equals to 20 times, now 10 raised to the power minus 6 divided by 100. That is going to give you 10 raised to the power minus 8. Which is going to have 10 raised to the power minus 8. So it's 10 raised to the power 2. 10 raised to the power 2. 10 raised to the power minus 6 divided by 10 raised to the power 2. If that 2 moves up, we change to minus. Then minus 6 minus 2 will give us minus 8. So this will give us 2.0 times 10 raised to the power minus 7 farad. That will be the capacitance of that capacitor. 2.0 times 10 raised to the power minus 7 farad. So this one is just a word to appetite. We have not actually gotten to the topic per se. We are still good. No, we are still good. Just calm down. We are still good. Now, take this down. Take down this question. Very, very important. Take down this question. Then you will solve it yourself. Obtain the capacitance of a capacitor. Obtain the capacitance of a capacitor that holds a total charge of 1 coulomb. That holds a total charge of 1 coulomb. If the PD across is 1 volt. If the PD across the capacitor is 1 volt, the capacitance will be 1 farad. Go and solve that yourself. Try and solve that yourself. Solve the question yourself. I know you can do it. The capacitance will be 1 farad. Capacitance will be 1 farad. Capacitance will be 1 farad. So try and do that yourself. What about if the PD across is 2 volts? Capacitance will reduce to 0.5 farad. So as this PD increases, the capacitance will be reducing. You can see it here. So you can check this very well. The capacitance is inverse relative to voltage and direct relative to charge. As the charge of the capacitor is increasing, the capacitance will also be increasing. So take note of that one. If the PD is increasing, the capacitance will be decreasing from this formula now. So take note of that. It's very, very important. Very, very important. So now let's go to the main business of today's class, which is types of capacitors. The types of capacitors we have. We have the following types of capacitors. We have the following types of capacitors. Number 1, parallel plate capacitor. Write it down. Parallel plate capacitor. Parallel plate capacitor. Write that down. Write that down. Parallel plate capacitor. Parallel plate capacitor. Parallel plate capacitor. Now, a parallel plate capacitor is just like a capacitor that has two plates, and the two plates will be separated by what we call, I remember I told you guys to separate the plates that complete a capacitor by what? Dielectric material. So the two plates will be separated by dielectric. I cannot be drawing here now because of time. So what I'm just going to do, I'm just going to define the relation of obtaining the capacitance. That's what we are here to do. How to calculate the capacitance of the capacitor, and not how to draw a capacitor. No. We are here to calculate. I will tell you the type of capacitor, and I will show you how to calculate the capacitance. That's what I'm here to do today. So you can browse capacitor and parallel capacitor. You see the picture. The picture will be showing up. The picture will be showing up. Alright, let's go. Now, the capacitance of a parallel plate capacitor. The capacitance of a parallel plate capacitor is defined as C is equals to epsilon naught A over D. Is defined as C is equals to epsilon naught A over D. Where dielectric constant is equals to 1. Now, let me just tell you this. If this dielectric constant is not equal to 1, before you apply this formula, if I give you a dielectric constant of the dielectric constant, let's say the dielectric constant is equal to 2, then the formula will be this K epsilon naught A over D. Then you now impute the 2 here. But for this time, we are assuming this K to be 1. So if you see a question under this capacitance of a capacitor, and they gives you the dielectric constant of a particular medium, please use the dielectric constant to multiply the answer after you have solved out without using the dielectric constant. So if you use this formula now to solve your question, you obtain an answer. So if there is a dielectric constant in the question, just use the dielectric constant to multiply the answer. You will get the final overall answer. So the answer will be increased a little bit by that value of that dielectric constant. So this is how you obtain the capacitance of a parallel plate capacitor, where C is equal to capacitance, of the capacitor. Remember, the capacitance of the capacitor is the ratio of what? Charge to what? Either voltage or potential difference. Take note of that. So if you solve this now, for a parallel plate, capacitor, you solve this equation, you are going to have this. That's what I'm trying to tell you. You are going to have this.
Alright, this is a picture format view of parallel plate capacitor. You can see the dielectric material and the two plates, and the capacitance equation that is given. That is how to calculate the capacitance of the capacitor. That's how it looks like. Thank you.
So what is C? C and this is still which is capacitance. That is capacitance. Now what is epsilon naught? Permittivity of free space, which is 8.85 times 10 to the power minus 12 coulomb square per Newton meter square. Take note. That is the unit of epsilon naught. Then what is A? A is area. That is area in meter square. That is unit. Take note. And D is the separation between the two plates, or the distance between the two plates. We call it separation because the distance should be very small. Because the smaller the distance, the higher the capacitance. Think of that. The smaller the distance, the higher the capacitance. But the smaller the area, the lower the capacitance. So if you reduce the distance, the capacitance will increase. If you reduce the area, capacitance will decrease. If you increase area, capacitance will increase. So capacitance is then for a parallel plate now, the capacitance is then proportional to what? The area, and inverse proportional to what? The separation. So if you reduce the separation of a parallel plate capacitor, the capacitance will increase. If you decrease the area of the capacitor, parallel plate capacitor, the capacitance will decrease as well. Take note of that. Inverse proportional to area, inverse proportional to distance or separation, then directly proportional to what? Area. If I say inverse proportional means an increase in one quantity will lead to decrease in the other quantity. That is the meaning of inverse proportion. But direct proportion means an increase in one quantity will lead to an increase. Inverse means an increase will lead to a decrease, but direct proportion means an increase will lead to an increase. The same. So that's how the thing is. So this one also in meters. That is the unit of the separation between the two plates. Obtain. Let's look at this question. Obtain the capacitance of a parallel plate capacitor. Obtain the capacitance of a parallel plate capacitor of 4 cm square. Of 4 cm square area. Of a parallel plate capacitor of 4 cm square area. Separated by a distance of 6 millimeters. Separated by a distance of what? 6 millimeters. Now, obtain the capacitance of a parallel plate capacitor of what? 4 cm square area separated by what? By a distance of 6 millimeters. By a distance of what? 6 millimeters. Area is what? Area is 4 cm square, centimeter square. So we are going to use it. We are going to use the area in meters square. So what do we do? Look how to convert this one. Now remember, if you want to convert from look at one way to do it. What is the meaning of 30 in physics? 30 means 10 raised to power minus 2. That is 30. There's what we call deci, centi, milli, micro, nano, Armstrong, pinko. Those are prefix used for some magnitude in physics. So this 30 is 10 raised to power minus 2. So if you square 10 raised to power minus 2, give you 10 raised to power minus 4. That's one way. Another lovely way. I love this way very well. If you want to convert from centimeters to meters, you divide the value by 100. That's how to convert from centimeters to meters. Now, if the centimeters is not squared, you also square the 100. That's how it is. If the centimeters is cubed now, cube the 100. So, if you want to convert from centimeter square to meter square, you will divide by 100 square. These two and these two are the same. But if you want to convert from centimeter to meter, divide by 100. 2 will still be there. That is a very good explanation of this. So even somebody that is late will understand that. So try and get it. Very, very important. So that will give us 4 times 10 raised to the power minus 4 meters squared. That's what we're going to have. Then the distance between the places will be 6 millimeters. Converting from millimeter to meter divided by 1000. We're going to have 0.6. We are not going to square somewhere because there's no square here. We're going to 0.006 meters. That's what I'm going to have. 0.006 meters. 0.006 meters. 0.006 meters. So if you solve this, we are going to have our capacitance to be epsilon naught A, which is epsilon naught is 8.85 times 10 to the power minus 12 A. What is 8? 4 times 10 to the power minus 4 divided by the distance between the places was 0.006. So if you do this, what are we going to have here? What are we going to have? We are going to have 5.9 times 10 to the power minus 13 farad. That will be the answer to that. So this is how to calculate the capacitance of a parallel plate capacitor. Now let's look at number 2. The second type of capacitor we have now. Now number 2, the capacitance of a coaxial cylindrical capacitor. Coaxial cylindrical capacitor. This is something like a type of capacitor that has something like superimposed cylinder. You have a very big cylinder, and you place another cylinder inside. It's a really two with dielectric materials. So, as I believe the capacitance of that capacitor also not look at 2 cylinders superimposed to each other. How to calculate the capacitance? We call it the coaxial cylindrical capacitor. So I'm going to have 2 radius, external radius, internal radius. Let's say this is the outer cylinder, this is the inner cylinder. So it's going to have a radius, so now we'll have what? Radius as well. So the radius of this outer inner we'll call it A, outer we'll call it B. That's what we'll call it. That's how we do it. So we have to calculate capacitance of this capacitor now. To obtain the capacitance of this coaxial cylindrical capacitor, this one is going to go this way. This way, maybe the inner one will go like that, go like that. So that's how it is. The cylinder is going to have length. It will have length as well. So the capacitance will be equal to 2 pi epsilon naught L over in B over A. This is how to calculate the capacitance of a coaxial cylindrical capacitor. This is a natural logarithm which is in, or logarithm to base E. So this is natural logarithm. This is the length of the cylinder. B and A are the external and internal radius respectively. I'm giving you a few speed. There's pi, which is 3.142. Pi is that 3.142, and you know, approximately. Then C is the capacitance of that coaxial cylindrical capacitor. Now, we have what we call C over N, which is called capacitance per unit length. Capacitance per unit length, or capacitance per length of the capacitor. This one will be equal to 2 pi epsilon naught over in B over what? E. Now, let's say they give you a question under coaxial cylindrical capacitor, and it asks what is the capacitance per unit length of this capacitor. This is how we are going to obtain the capacitance. We're going to obtain the capacitance this way.
Alright, this is a picture format view of coaxial cylindrical capacitor. As you can see, the two cylinders, one is placed inside the other. This is how it looks like.
So let's look at this question. Let's look at this question to see what we are going to have. For a coaxial cylindrical capacitor. Remember, first capacitance per unit length, that is over length. Position per unit length, that is the capacitance, general capacitance. So that is capacitance per unit length for a coaxial cylindrical capacitor. External radius, the length, the capacitance. In means natural logarithm. So a coaxial cable, take this question down. A coaxial cable of length 2 meters. A coaxial cable of length 2 meters has internal diameter. Let's call that D2, D1, let's call that D1. Internal diameter of 1 millimeter and external diameter of 2 millimeters. Of 3 millimeters and external diameter of 3 millimeters. External diameter of 3 millimeters. Obtain the capacitance of this cable. Obtain the capacitance of this cable. If we are to treat it as a coaxial cylindrical capacitor. So we are going to obtain the capacitance of this cable now. If it is cylindrical in shape and is acting as a coaxial cylindrical capacitor. So let's look at it. Let's see what we're going to have. Now, the internal radius will be the diameter over 2, which is 1 over 2 is what? 0.5 millimeters. So divided by 1000 divided to meters, we will have 0.0005 meters. Then the external diameter will be, the internal radius will be the second diameter, the internal diameter over 2, which is 1.5. Measure by 1000 divided to meter, from millimeter to meter, divided by 1000. We're going to have 0.0015 meters. That's what we're going to have. Now, let's substitute these values now into this general formula. We are not going to calculate the capacitance per unit length. We are going to calculate the capacitance of this capacitor. So we are going to use this one now. So C will now be equal to 2 times 5, which is 3.142, times 8.85 times 10 to the power minus 12 times L. And what is L? L is what? 2. Divided by in of B over A, which is 0.0015 over 0.0005. So you solve this very well with your computing devices. Take your calculator, you see in there. There's in your calculator. Your cash calculator has in there. So this will give you 1.012 times 10 to the power minus 10 farad. Or you can also say 1.012 Armstrong farad. Why is it Armstrong farad? Because Armstrong is said to have 10 to the minus 10 in physics. Armstrong is the prefix we do give to the magnitude is 10 to the minus 10. Also call it Armstrong. This one is Armstrong. This one means Armstrong. 10 to the minus 10 means Armstrong farad. That's how I'm writing that one. Armstrong farad. So that's how we calculate the capacitance of a coaxial cylindrical capacitor. Now let's move to how to calculate the capacitance of the third one. We have the third capacitor here. The third type of capacitor, third one, a spherical capacitor or concentric sphere capacitor. That is the next one we are going to look at now. Concentric sphere capacitor. Concentric sphere capacitor. Concentric sphere capacitor. Concentric sphere capacitor. Now this is just like we have two spheres, just like we have two cylinders joined together here. Two spheres also joined together. One sphere will be placed inside another sphere. How to calculate the capacitance of such a sphere? So how will you do that? To obtain the capacitance of a spherical capacitor, we use the relation that the capacitance will be equal to 4 pi epsilon naught AB over B minus A. Now, in some tests, you see this way: arrow A, arrow B over arrow B minus arrow A. Some tests you see this way: arrow A, arrow B over arrow B minus what? Arrow A. Now, arrow A is said here as internal radius. That of arrow A, inner radius. Inner radius, that is arrow A. Then arrow B is external radius or outer radius. Not diameter again now, radius. So we will say AB, BA. They means radius here, radius. So not diameter. So think about that too. So this is the internal radius or inner radius. That is the external radius or outer radius. Take note of that. All that in C is capacitance, pi, epsilon naught, give you up space already known. So this is how you calculate the capacitance of a spherical capacitor. Take note. It's very, very important. It's very, very important.
Alright, this is a picture of a concentric conductive sphere capacitor. You can see the picture. That is how it looks.
Okay, let's look at a very good question under this so that you see it. Obtain the capacitance of a spherical capacitor. Obtain the capacitance of a spherical capacitor. Obtain the capacitance of a spherical capacitor. Obtain the capacitance of a spherical capacitor of radii arrow A equal to 20 cm and arrow B equal to 25 cm. Of radii arrow A equal to 20 cm and arrow B equal to 25 cm. So how we calculate the capacitance of this capacitor now? The capacitance will be equal to arrow A in meters to be 20 over 100. Remember, when we go back from cm to meters, divide by 100. That will give us 0.2 meters. Arrow B will be equal to 25 over 100. This will give us 0.25 meters. That's what we're going to have. Then the capacitance will now be equal to 4 times pi. What is pi? 3.142 times 8.85 times 10 to the power what? Minus 12 times arrow A is what? 0.2 times arrow B is what? 0.25. That's arrow B. Then over arrow B minus arrow A, 0.25 minus 0.2. So if you solve this very well with your show calculator, you are going to have 1.11 times 10 to the power minus 10 farad. Or you can call this 1.11 Armstrong farad. So these are your compute or evaluate where problems that involves spherical capacitor. Now let's look at the fourth one. Fourth one, which is the last one we'll be looking at now today in today's class. The four types of capacitor. Remember, we have looked at parallel plate capacitor. Take note of the formulas. Very, very important. I looked at parallel plate capacitor. I looked at coaxial cylindrical capacitor. We look at spherical or concentric sphere capacitor. Now we want to look at isolated sphere capacitor. That is the next one. Isolated sphere capacitor. Isolated sphere capacitor. The capacitance of an isolated sphere capacitor. The capacitance of an isolated sphere capacitor is defined as C equal to 4 pi epsilon naught A, where A is equal to radius. Where A is equal to radius of the sphere. Where A is equal to radius of the sphere. So some people can also write it this way: C is equal to 4 pi epsilon naught R. Some people can also write it this way. It will still be correct. Now remember, if dielectric constant is inside, you multiply this E naught by that, or multiply the final answer by the dielectric constant. Take note of that. So this is how you define the capacitance of an isolated. You just check the name, an isolated sphere capacitor. And I do this way: A means radius, or you that way where R means also radius. Let's answer this question. Obtain the capacitance of an isolated sphere. Obtain the capacitance of an isolated sphere of radius 30 cm. Of what? Radius 30 cm. Obtain the capacitance of an isolated sphere of radius 30 cm. Very simple. Radius is this, which is what? 30 over what? 100. That was 0.3 meters. Oh, this is going to give us capacitance will now be 4 pi epsilon naught. Very simple formula, it's a very simple one, times 0.3. So if you solve that very well, we are going to have a very good answer. But this is a very simple formula to use. It's very simple. So this one is going to be 3.35 times 10 to the power minus 11 farad. So before we go, there's something very important we should also like to look at, which is energy. How to calculate the energy stored in a capacitor. How to obtain the energy stored in a capacitor. Now, you remember that, or you can recall that energy is the ability to do work. I don't know if you can still remember that. Energy is the ability to what? Do work. Dimensionally, energy and work done are the same thing. They are the same. Dimensionally, energy and work are equal. Energy is not the ability or the capacity or the intensity to do work. So the energy stored in a capacitor is divided by W, or U. Someone can also use U. Either use W or use U, anyone you like. Is equals to half CV squared or half Q times V, depending on the quantities you are having. Where C is capacitance, V is potential difference or voltage, Q is charge. Remember, Q is equal to CV. Remember something. C is equal to Q over V. From here, Q will be equal to what? C times V will be what? CV. So Q is equal to CV. V is equal to Q over C. Just change the subject formulas. So now, I can give you a question. I'll say, what is the energy stored in this capacitor? Let's say we have this capacitor now, and we pass a PD, potential difference of let's say 10 volts across this capacitor. So what is the energy stored? Just use this one. Just use the capacitance to multiply the potential difference squared and multiply by half. We have the energy stored in the capacitor. So before we look at a typical question under this, let's look at how to combine capacitors. Combination of capacitors. Let's say we have 1, 2, 3 or more than one capacitors in a cycle. How do you combine them together? Now recall that, or take note of this. The symbol of a capacitor is this. This is a symbol for a capacitor. If one terminal is negative, the other terminal will be positive. So one terminal will be negative, the other terminal will be positive. Remember, for a cell, we do for a cell, one terminal will be longer than the other. We'll do that when we get to current electricity. Think of that. So this is a symbol for capacitor. Think of that, electronics. And you can either take of this combination of capacitor. Now, capacitors can either be combined in series or in parallel. Capacitors can either be combined in series or in parallel. They are combined in series if they don't have common endpoints. Take note of that. They are combined in series if they don't have what? Common endpoints. For example, let's say we have the following capacitors combined. Let's say we have capacitors. This one, C1, combined with another capacitor, C2, then combined with another capacitor, C3, and so on. You say, what is this? This one is C2, this one is C3. So what is the total capacitance of these capacitors now? And check. This one is starting from this place and it ends somewhere here. So this other one will start here and end somewhere here. This other one will start here and end somewhere here. You check now. They don't end and start
at the same place.
Now, to get the equivalent capacitance or to get the total capacitance of these capacitors combined in series now, we're going to do it this way. 1 over their total, we call it C equivalent, will be equal to 1 over the first one plus 1 over the second one plus 1 over the third one until you get to the last one. That will be the way to combine, if you want to combine these capacitors. So this one will be the total capacitance of this capacitor. Now, number 2, parallel combination. Capacitors are said to be combined in parallel if they have common endpoints. If they have what? Common what? Endpoint. They have common endpoint. Look at what I'm trying to say. Let's say we have this capacitor here. We have this capacitor. We have this. Take a look at this. We have this. We have this. And we have this. So this is C1. This is C2. This is C3. So this we have these capacitors. We have these capacitors. And we want to combine them now in another way. Now I can combine this with this, connect it with this, connect this with this, connect this with this, connect it here, connect it here. If you check remember, you discover that 1, 2, 3 started from this place. They are ends. They are both ends is at this point and this point. There's no other end again. So that means they have common end point. They end at the same point. So this first one started from this place ends here. This one started from this place ends here. This one started from this place ends here. You have common end point. And to obtain the total capacitance of these capacitors, or the equivalent capacitance will be this way. C equivalent equal to C1 plus C2 plus C3. Just add up that one. Don't take the inverse. For series, we take the inverse of the capacitance of parallel, just add them up linear without taking any ratio. So that's how we do this. So take note of this. When we get to electricity, I will explain more. There's something called resistance in current electricity. Now for resistance, parallel we take this, series we take this here. So but this for capacitors, parallel we're going to combine it this way. And series we combine this way for capacitors. Then parallel we combine this way for capacitors. Now let's look at this question. Very good question. Very good question. Are we good to go? Alright. Alright, take this on. 2 capacitors, C1 equal to 3 microfarad and C2 equal to 5 microfarad are combined in series. Combined together in series. 2 capacitors, C1 equal to 3 microfarad and C2 equal to 5 microfarad are combined together in series across a 9-volt battery. That is the potential representing or the voltage of the battery across a 9-volt battery. Obtain their equivalent capacitance and the energy stored in the capacitor. Obtain the equivalent capacitance and the energy stored in the capacitor. Solution. Look at it. Solution. Now, these capacitors are combined in series. They are combined in series. So 1 over, I'm going to use this. 1 over C equivalent to be equal to 1 over the first one plus what? 1 over the second one. That just swap them. You end it there. It's 1 plus 3. So this will give us 1 over C equivalent will be equal to 1 over first one is 3 plus 1 over second one is what? 5. So the next thing we're going to do, what is the LCM of 5 and 3? The LCM is what? 15. That's the LCM of 5 and 3. So 15 divided by 3, 5. 5 times 1, that will give us 5 plus 15 divided by 5, 3. 3 times 1, 3 times 1, 3. So this will give us 5 plus 3. We have 8 over 15. 8 over 15. 8 over 15. So our 1 over C equivalent, will be equal to 8 over 15. So from here, you can either cross multiply C equivalent times 8, 15 times 1, then you make C equivalent the subject of the formula and look for the value of C equivalent of total capacitance. Or you can also do it this way, because I love this way very well. I don't use complication, I use lovely way or very short way. I will call it my sweet shortcut. Look at it. What I will just do, I will just take the reciprocal on both sides. You bring C equivalent to the upper side, then bring 1 to the downside. Bring 15 to the upper side, move 8 to the downside. Let's try it. Bring C equivalent here, we will have C equivalent. Bring 1 to the downside, we will have 1. Bring 15 here, we will have 15. Bring 8 here, we will have 8. Same thing, you are still going to get it from the group of equation. Then this will give us C equivalent equal to 15 over 8. So if you do this, you are going to calculate what are you going to have in decimal format, decimal fraction. Then what will be the energy stored? Half CV squared. I'm going to use U as a symbol for energy now. Remember, energy stored is that W is equals to half CV squared, or you can also say U is equals to half CV squared, or you can also say U is equals to half QV, or say U is equals to half QV, depending on the symbol you want to use. Now, W denotes energy, U also denotes energy here. So you can use any symbol, but I'm going to be using U as my energy here. So C means capacitance, Q means charge, V means voltage or potential difference. If you look at this formula now, we have, look at this question, we have the capacitance, equivalent, the total capacitance of that capacitor, already have it here, which we will put here. We have the voltage of the battery, we will put here, there's no charge, so we will not use this, we are going to use this one. That's why I'm putting that. So if you input the values now, what are you going to have? So let's run with a calculator to see what we are going to have. Let's try to calculate to see what we are going to have. Alright, if you do this with your calculator, this over 15 over is going to give us 1.875 microfarad. Remember, micro is 10 to the minus 6, then we have farad. So if you substitute this C into this place, and this 9 into this place, you're going to have this 9 square. Multiply your calculator, you will have this as your final answer. So this is how we run capacitance on capacitor. Although we have some other questions in capacitance, you should also look at. But I hope you are blessed into this class. So if there's anything you don't understand in this topic today, go back and watch this video over and over again. Watch it at least 5 times. We grab everything from like to the fullness. And if after watching it over and again, there's some stops or still grey head you don't know, then you can drop your question in our comment section and look at it later. This is capacitance of a capacitor, and most of the things you need to know about this topic. So please ensure you dedicate your time to this. Don't allow it to distract you. Just go back again now, watch this video again. Watch at least 3 times, 4 times. When you know it's already very good in this topic. I want to be good in this topic. That's why I'm doing it. So please try your best to devote your time to the topic. See you guys in our next class. I love you all. God bless you. Thank you. Thank you.